and get started with this. I'm a minute early, actually, but that's okay. It's going to be 2:30 really soon, like right now. No, okay. So how does a buffer solution resist a change in pH? So we're just going to go over the pre-lab questions, and just to remind you of how I want you to write up this first part, I just want beginning question, and then I want you to look at the explanation to strengthen student understanding to get some background information. And then also in the what background information do I need to know, I want you to answer the pre-lab question. So that's what we're going to go over now. And there's actually quite a bit to the pre-lab. It'll maybe take you, I'm debating whether to walk you through all of this or not. I guess it sort of depends on whether this simulation works on the Chromebooks or not. I'm going to pause the video for a second because I just thought about that. Okay, we have just confirmed that it actually works on the Chromebooks. So I'll walk you through this a little bit less, actually, as far as the animation stuff, because I don't know that you'll need all that much help with it.
Thank you.
Okay, so first question here: how does a buffer solution resist a change in pH? Do we need to talk about that one, or did we talk about that enough in class that you feel okay about that? I mean, basically, the main answer there that you need to give is that a buffer solution contains both an acid and its conjugate base, right? So if it has an acid in there, the acid can react with any base that you add, neutralize it, so that there's not that much of a change in pH. Because if you think about it, change in pH is going to happen because of a a higher or lower H3O plus concentration, or H plus concentration, however you want to think about it. So let's say that I've got acetic acid, a buffer with acetic acid and sodium acetate in it. All right, so basically my my buffer solution here is involved with this equilibrium. I'm taking a shortcut method here, okay? But I have, let's say, roughly equal amounts of both of these things in the solution, right? So let's say then I decide that I'm going to add some sodium hydroxide into this solution, some NaOH. All right, so I put in the NaOH. Well, now I've got these OH minus ions running around in the solution, that what they would normally do is they would react with this H plus, take some of the H plus out of solution, so then the pH gets higher, because now we've got a lower H plus concentration, right? But what they can do in this buffer solution instead, yeah, I knew that wasn't going to work. Oh well. What they can do in this buffer solution instead is these OH minus ions will react with the acid, okay? And when they react with the acid, this hydrogen comes off, and now you've got H2O, and then you've got this, the C2H3O2 minus, right? So we didn't really do a whole lot to this right here, which allows the pH to stay approximately the same. Does that kind of make sense? All right, same thing if we add, it's annoying. If we add an acid to this, okay, so I add an acid like HCl, strong acid, okay? That dissociates into H plus, Cl minus, right? Normally, this H plus would increase the H plus concentration of the solution, which would decrease the pH. But in this case, because we've got significant amounts of a base here, this H can actually react with the C2H3O2, sorry, that's supposed to be a minus, C2H3O2 minus, make HC2H3O2. And now we've just increased our concentration of this, but we didn't really change the H plus all that much. So again, the pH doesn't change by a very significant amount, okay? Now, as long as you've got some of the acid, some of the conjugate base in that solution, everything's going to be fine, okay? Now, if you What you're eventually going to do, if you dump enough of the HCl in there, then you will change all of that C2H3O2 into the acid, right? At that point, there is no more base, so if you keep dumping in the H+, now it is going to increase the H+ concentration because there's no more base there to react with the H+, okay? And same thing with a base. If you add enough base in, eventually you've converted all of the acetic acid into acetate. And at that point, you keep adding in OH-, and now the only thing it has left to react with is the H+. So it's going to take some of the H+ out of solution and increase the pH. Okay? So that's why a buffer solution resists a change, and that's maybe a little more in detail than I went in class. That's definitely more detailed than I went in class today. Why would HCl and NaOH be poor choices for an acid-base pair to make a buffer? Okay, so let's just think about what we just talked about. Let's say I've got a reaction here, HCl and NaOH. So I put both of those into a solution. Well, what's going to happen here is that the HCl is going to dissociate into H+ and Cl-, right? The NaOH is going to dissociate into Na+ and OH-. The Na and the Cl aren't going to really do anything in the solution, right? Because you've got an alkali metal and you've got the conjugate base of a strong acid, so those aren't going to do anything. But now I've just got a bunch of H+ and OH- running around in the solution. They react with each other and make water. And, you know, then you dump anything else into there, and it didn't help at all because we don't have any of the acid or base left. They, you know, the H+ and the OH- reacted to form water. Okay? So it doesn't work as well. It doesn't work basically at all when you're using a strong acid or a strong base as opposed to weak acid and its conjugate weak base. All right, so then it tells you to go to the animation. Pause this. Okay, so the animation should look like this. And basically the way that this works, and I think it's pretty self-explanatory, but, oh, I need to go back to part 1. So it's going to look like this to start with. And so what it tells you to do first is choose the HNO3 and the NaNO3, I think, as the buffer solution. Now, they put buffer solution in quotations because some of these are not going to be good buffer solutions, and then some of them will be. So they're saying to put those two in a solution together, and then I think you have it set to, the weird thing about this, I don't know why they do it this way, but it's, the molarity is 10, but then it's 10 either times 10 to the negative second, or 10 times 10 to the negative first, which basically translates to, if you have it on this top one, it's 0.1 molar, and then if you have it clicked on the bottom one here, then it's 1 molar. Okay, so again, I don't know why they do it that way. They say to keep the volume at 100 milliliters, and then you just put in the probe, and it should give you a pH reading. And that one is 1.30. That one's hard to see, but it's 1.30 on that one. Okay, and then you can remove the probe that way, and then you can go to part 2, and then they're telling you basically to put in a certain amount of HCl, and I think you just keep it set for the default at first. And you put in that, and you see what it does to the pH, and it looks like it goes down a little bit more, down to 1.25. Okay, so what they're basically having you do is work your way through this thing. Just follow the instructions and fill out the chart that it tells you to fill out. And so then you're doing the same thing for the acetic acid and sodium acetate, and then ammonium chloride and ammonia. And then it says increase the molarity by 10 times. Now all this is in the instructions up here. It says remake the buffers using the same volumes, but this time 1 molar components instead of 0.1. And then you're adding the same amount of HCl and NaOH to the stronger buffers. In other words, more concentrated buffers. Okay, and then finally repeat the process, and now you're adding a higher amount of strong acid and strong base, and completing the last 3 lines. And so then you're just basically going to see what happens there. Okay, so then you'll get down to 3A and B. And A says, write a general chemical equation to represent the equilibrium that exists in the aqueous system of the weak acid HA that ionizes in water. Assume the weak acid to be acetic acid. What's the pH? So basically what you're doing here, first they just want you to write a general equation for a weak acid, which is easy. We've done this several times already. It's going to dissociate into H plus and A minus, but it's going to be in equilibrium, because that shows that usually we probably stay with this particular form. It doesn't dissociate. But then they're giving you some actual concrete numbers. They're saying if this is acetic acid we're talking about, and the Ka value is 1.8 times 10 to the negative fifth, and they give you an initial concentration, they want to know what is the pH. And that's basically what we did on the last test. Okay, so you've got an acid, weak acid in equilibrium, and we're trying to figure out what's the pH of that solution. Then it asks you, so I'm going to let you calculate that on your own, because you basically just make an ice table for that one and figure it out. Then it says, what is the addition of NaC2H3O2 due to the equilibrium you just represented? Okay, so I don't know why they have you write it as a general equation and then they start talking about acetic acid, but if we've got if that's our equilibrium, then to put in the sodium acetate, essentially what we're doing is we're adding more of this. So just thinking in terms of Le Chatelier, all they're asking here is really what would it do to the equilibrium. So they're just asking in general terms, and it would push it back this direction, right? Which would actually make the pH lower, because it's going to lower the H plus concentration in the solution since it's pushing the equilibrium back towards the left side. It means less of this H plus is going to come off, and so then your pH ends up being, did I say it lower the pH? If I said lower the pH, I meant it's going to increase the pH because it lowers the H plus concentration. So, so that's kind of what they're looking for on that part of the question. Then it says use these chemical principles to explain why the first pH is so much larger. The first pH recorded from the simulation is so much larger than your calculated value for pure 0.1 molar acetic acid. Okay, so the first pH recorded from the simulation, wait, is so much larger? Oh, okay. They're talking about the pH recorded from the acetic acid part of the simulation. And if you do that, the pH of that buffer solution, when you have equal amounts, I think it ends up being about 4.74 for the pH. So they're asking you to explain why is it that pH is so much larger than your calculated value for pure 0.1 molar acetic acid. So when you calculate up here using your ice table, you should get a much lower pH than that for just pure acetic acid. But then they're wanting to know why is it that when you have the acetic acid and the sodium acetate together, why does it have so much higher of a pH? And that should be fairly obvious based on the Chatelier, which we just talked about, pushes it back to the left. So lower H plus concentration, which makes a higher pH. But then also, I mean, C2H3O2 minus is a weak base. So you dump a weak base into a solution, it's obviously going to raise the pH of the solution, right? So I think either one of those ways is a good way to think about it. How do the pKa values for acetic acid and ammonium compare to the pH values for the first two buffers in the simulation? Once you work your way through the simulation, and I don't know this for absolute sure, but I am guessing that what you're going to end up with is that the pH values you get for those buffers is equal to the pKa value. All right. So when you look at acetic acid and you look at the ammonium ion, now they gave you the Ka for acetic acid already up here. It's 1.8 times 10 to the negative fifth. Okay. So you find the pKa of that number check this to make sure. Give you 4.74, which I just said, but I'm pretty sure the pH of your buffer solution there is 4.74, okay? So if you take the negative log of your Ka value, it actually equals the pH of your buffer solution, okay? And then same thing's probably going to happen for the ammonium ion, okay? Your pH for that one, if you take the negative log of this 5.6 times 10 to the negative 10th, you get 9.25. So my guess is the pH of that solution when you find it is going to be 9.25. And the reason for that phenomenon, probably the easiest way to explain it is just to talk about Henderson-Hasselbalch. pH equals pKa plus the log of A minus over HA. And what you're doing in all of these buffer solutions on the website, part 1, you're using the same molarity for each of these, right? So you have the same concentration of acid and conjugate base. And when that's the case, then over here, you've got, you know, A minus and HA are equal, so that becomes log of 1. Log of 1 is 0, so this whole term goes away, and at that point, pH equals pKa. So that's why you're seeing that phenomenon. And then why don't pH values change when the component concentrations are increased? Okay, so remember, the pH values, so you're going to notice this when you do the activity as well, that the pH values actually don't change. It's because it's the ratio, right? So it doesn't matter if you have 0.1 up here for A minus and 0.1 down here for HA, or 1 and 1 for those two numbers. The ratio is still the same, so the pH is still going to be the same. Okay. Okay, so then number 4, write a general equation to show how a buffer containing an acid HA and the salt of its conjugate base would respond to the addition of each of the following. Okay, now I sort of already did this, but this is a useful exercise here. So we've got HA and the salt of its conjugate base. So really what we have in this solution is HA, and then we have A minus, okay, in that particular buffer solution. So if we put HCl into it, really what we're adding is more H plus, right? So the H plus is going to react with what here? It's going to react with the base, right? Because the H plus is the acid, so it's going to react with the A minus. So if we put H plus in here, it's going to react with the A minus, and it's going to make more HA. Now, I'm just using a forward arrow there, okay, because this is a strong acid, right? So this isn't going to go backwards. When we add a strong acid, we just do forward arrows, and that's it, okay? So then when we add the strong base NaOH, again, that dissociates, and the only thing we really care about here is that we're adding OH minus into that solution. What's the OH minus going to react with? The HA, right? So the OH minus plus HA, the H is going to come off of the HA and make H2O, make water. And then we're going to end up with more A minus, okay? So if you think about it, the reason that the pH changes even a little bit before your buffer solution has really run out or reached its capacity is because if you're thinking about it in terms of this formula, when we dump acid in, what we're doing is we're increasing the concentration of the HA and we're decreasing the concentration of the A minus, right? So we are changing these two numbers a little bit. Now because it's a log, that sort of smooths things out a little bit, and it makes a fairly large change look fairly small, okay? Just because of that logarithm function there. But we are changing those concentrations. And then same thing with the bottom equation. We're actually making more A minus and decreasing the amount of HA. So we're changing this ratio right here, even before we get to a point where we've completely run out of one or the other. Okay? As soon as you run out of one of these, at that point you're just dumping extra H plus into the solution, or you're dumping extra OH minus in the solution, and that determines the overall pH. Okay, which we're going to talk about that more once we get to titration, the titration stuff in 17.3. Okay. Why are the pH changes so noticeable with the last two additions of strong acid and base in the simulation? I think the simple answer there is we're adding more of the strong acid and strong base, right? So what you're going to notice is that your capacity at that point makes a difference, right? So how much of the weak acid and conjugate base you have is going to make a difference, okay? And which of the two concentration combinations would be most effective for an antibiological agent's buffer? Which of the two concentration combinations? Okay, so they're asking about here. I think what they're asking here is, would the 0.1 concentration, 0.1 molar concentration, would that be the best combination? Or would this be the most effective combination when we're using the 1 molar concentration? I mean, the answer for that is probably fairly obvious, right? It would be the 1 molar, because you can add more of the acid or more of the base into the solution when it has the higher concentration before the pH starts to drastically change, okay? Now, there is something kind of weird with that question. It's asking about an anti-biological agent's buffer. So if you go back to the beginning, the context of the investigation, what you're actually doing for this one is you are, let's see here, company contracting your chemistry class aims to produce a variety of bacteria designed to destroy harmful living agents. And the bacteria must be grown in a medium with a pH that's similar to the environment they will be functioning in. Okay, so that's why they're talking about anti-biological agent buffer, because that's actually what we're trying to design here. Okay. All right, so I think that's pretty much it for the pre-lab questions. You're just going to have to, the bulk of your work now is just going to be to go through that simulation and fill out the chart. Okay. Then hopefully everything else should make sense based on what we just discussed. Okay, we'll see you in class tomorrow.